Jai Hind. Myself R.P. Singh, Assistant Professor, Department of Electronics and Communication Engineering, AKGEC, Ghaziabad. Today we are going to discuss MOSFET operation and its characteristics. If time permits, then we will also discuss about effect of channel length modulation, and we will try to derivate current equations as well. So, if we talk about the MOSFET, so MOSFET is also called as MOS transistor. If we talk about its application, then MOSFET is used as a basic building block for all kind of integrated circuits. If we want to make amplifier, then MOSFET can be used. With the help of MOSFET, we can make semiconductor memories, RAM, ROM, and so many applications are there. If we talk about the structure of the MOSFET, then as name suggests, in the name of MOSFET, first three letters MOS. M is metal, O for oxide, S for semiconductor. So, as a part of semiconductor, the base, this region, this is called as base or body. This is basically semiconductor. Either we are using N channel MOSFET, either P channel MOSFET. If we are having N type MOSFET, N channel MOSFET, then this substrate will be P type silicon. So, here I am taking reference as P substrate. So, this body or this substrate is P type semiconductor. I am taking silicon for my reference. Some other kind of semiconductor may also be used, but nowadays we are extensively using silicon as substrate. So, at the base P substrate, above P substrate, there is oxide coating. So, this is the silicon dioxide layer. A thin silicon dioxide layer is grown above the silicon substrate. So, at the base we have silicon substrate. This is silicon. In fact, P type silicon semiconductor is used. Above silicon substrate, a thin layer of oxide is grown. This layer is basically layer of silicon dioxide. In the diagram, you can say that you can see this is the layer of silicon dioxide. This is basically insulating layer which is grown above the substrate. Above the oxide layer, metal gate is created. So, here by the black color, the metal electrode is shown. Initially, we have used aluminum for the metal gate, but nowadays we are using polysilicon, but we are using the name MOS, metal oxide semiconductor, because initially it was used. For growing the MOSFET, we have created two N plus diffusion regions. So, here N plus diffusion regions, this is N plus region, this is also N plus region. Both these regions are identical to each other. Doping is equal, structure is equal, and MOSFET is symmetrical with drain and source. Any terminal can be treated as a source, any terminal can be treated as a drain, depending upon the potential. If we have higher potential at this region, then it will act as a drain. If this potential has lower potential, then this end can be act as a source. So, depending upon the potential, any diffusion region can be treated as drain, either can be treated as source. So, in this diagram, this is drain, this is source. At the base, we are having substrate and a metal oxide, and some metal contact is made above the N plus diffusion region. Abbreviation S is used for source, abbreviation G is used for gate, abbreviation D is used for drain. And to show the substrate, we are using B, because the substrate is also called as body. Substrate is basically the base at which the entire MOSFET is grown. So, if we talk about metal oxide semiconductor structure, then in metal oxide semiconductor structure, conducting channel, that is also known as inversion layer, is eventually created with the effect of gate biasing, and this channel is created between this source and drain region, and the length of channel is called as L. If the channel is already present at the time of fabrication without applying any gate voltage, then such kind of MOSFET is known as, if channel is already present at Vg is equal to 0, then the kind of MOSFET is known as depletion time MOSFET. If channel is not present and it will be enhanced by applying certain gate voltage, then the kind of MOSFET is known as enhancement type MOSFET. So here I am using the whole terminology. I am taking enhancement type MOSFET for my own example. Depletion type MOSFET can also be explained with the help of these structures. Now come on to the circuit symbol. So these are the circuit symbols for the N channel MOSFET. This is the 4 terminal structure, 4 terminal symbol, gate, drain and source, and this arrow basically indicates the flow of carriers. This is the simplified symbolic representation for N channel MOSFET, and this is for P channel MOSFET. For simplified representation for N channel MOSFET, we are using such kind of symbol. For P channel MOSFET, we are using bubble at gate terminal. So this is the difference between P channel and N channel MOSFET. Now come to the structure of N channel MOSFET again. I am again taking this diagram. It's basically 1D diagram. So with the help of this diagram, we can explain the working principle, and we will study the qualitative description of N channel MOSFET. So in this structure, we can see that the N plus terminal is treated as source, this N plus terminal is treated as drain, and this is gate terminal, and the thickness of oxide is indicated by TOX. Basically this silicon dioxide layer is very thick, order of nanometer, and the thickness of this silicon dioxide is from 1 nanometer to 10 nanometer. So this is the thickness of this silicon dioxide layer. Since it's very thick, so sometimes it is also called as thin ox. It is also called as thin oxide layer, thin ox. And the current conduction taking place via channel. So if there is no any voltage is applied, then there will be no any conduction, because this is the N plus region, it's a P region, and between P plus and N region a depletion region is created, and there will be no conduction. So in this diagram we have shown some biasing conditions for the qualitative description of MOSFET working. Source is grounded, so source voltage will be 0, and all other potentials will be taken with reference to source terminal. Gate terminal is applied to a positive terminal, so VGS is positive, gate to source voltage is positive, and drain is grounded. So in this structure, source is grounded, so VS is 0, VGS is positive, but the value of this positive is voltage is small. VGS is positive but small, and VDS is equal to 0. At this situation, when Vg is greater than 0, so if we have applied positive potential at the gate, then because of this positive potential, the holes in this p-type substrate will feel some repulsive force. Because of this repulsion, holes will go deeper inside the substrate. They will leave some uncompensated immobile ions that are basically known as acceptor ions. So a depletion region is created between N plus drain, N plus source, and P substrate. So a depletion region is shown by the white color. So this is the depletion region. In this region there will be no mobile carriers, there will be no holes, there will be no electrons, only we are having some acceptor ions. So no electron can flow from source to drain because of this depletion region. So because of depletion region, current conduction is not possible. And MOSFET can be said to be in off condition. So, it is a basically cutoff condition where current is not flowing. So, when VDS is 0, then ID will be 0. This is basically cutoff region. Now, for the conduction process, we need to create a channel between source and drain. To create a channel, we have to apply positive gate to source voltage. The positive gate voltage on the gate causes, in the first instance, the free holes which are positively charged to be repelled from the region of the substrate under to the gate. So, in this diagram, we can see that the positive holes are repelled back inside the substrate, and this depletion region is basically devoid of any kind of carriers, and there are only acceptor ions are present and depletion region is created. So, there will be no conduction. As this positive voltage will be increased, if we increase this positive gate voltage, then the effect of positive gate voltage, some electrons will also be attracted above. So, in this diagram, we have increased the positive gate voltage. By increasing positive gate voltage, this gate voltage will attract electrons from source as well as electrons from the substrate, and some electrons come onto the surface of silicon dioxide and silicon interface. And as we are increasing gate to source voltage, at a certain value of positive gate to source voltage, at a certain value of VGS, the entire channel region is inverted by the holes, and a inversion layer, a channel, is created from source to drain. From source to drain, we are having a layer of electrons. So, this inversion layer is also known as conducting channel. With the help of this channel, a conducting path is created between source and drain. The value of VGS, yani the value of gate to source voltage at which surface inversion is created, is called as threshold voltage. So, threshold voltage is basically the voltage beyond which the channel is created and MOSFET can conduct. So, this is the necessary condition for the conduction of the MOSFET. Without VGS greater than VT, MOSFET cannot be conduct. To conduct the transistor, we have to create surface inversion. To create the surface inversion, we have to apply VGS greater than or equal to VT, either greater, either equal. So, again I am repeating, the value of positive gate to source voltage for the n-channel MOSFET, it is a positive. The value of gate to source voltage needed to cause surface inversion, in fact to create conducting channel, is called as threshold voltage. So, when the VGS is greater than VT, in fact the VGS is greater than threshold voltage, either equal to threshold voltage, then in this situation a positive a channel is created between n plus source to n plus drain. It means electrons are available at the surface underneath the gate terminal. So, we are getting this surface is inverted by the electrons. So, in the MOSFET fabrication process, the value of threshold voltage can be varied by selective doping. In most MOS fabrication process, the threshold voltage can be adjusted by selective dopant ion implantation into the channel region of the MOSFET. For n-channel MOSFET, the threshold voltage is increased by adding extra p kind of impurities. Alternatively, the value of threshold voltage can be lowered, can be made more negative by implanting n-type impurities, n-type dopant atoms. So, the value of threshold voltage can be adjusted at the time of fabrication itself. So, if after the fabrication of the MOSFET, the value of threshold voltage cannot be varied. So, it is a basically device characteristics. So, now come to the further study of MOSFET operation, MOSFET behavior. When VGS is greater than 0 but less than threshold voltage, yani VGS is, it means VGS is less than VT but greater than 0, means positive VGS is applied. there will be no channel, there will be no conducting path between source and drain exists, so there is no any possibility of current conduction. Now, when the VGS is greater than VT, here it is represented as VT naught. This naught represents there will be no biasing of substrate. Substrate is not biased, it means this substrate terminal is connected to ground. If VB is 0, then the threshold voltage can be written as VT naught. This 0 represents there will be no substrate biasing. Substrate is biased as 0 voltage. So, terminology VT0 is used. Either we can use VT. VT means substrate is biased at certain value. So, when VGS is greater than VT naught, means gate to source voltage is greater than threshold voltage, then in this condition a channel is created. Channel is created means current conduction can be made, but VGS greater than or equal to 0, in fact greater than or equal to VT, and VDS is equal to 0. If VDS is equal to 0, then current conduction is not possible, because we have to create some potential difference between two terminals, between drain and source. Without creating any potential difference, without applying VDS, current conduction is not possible. So, for the conduction of the MOSFET, we have to apply VDS greater than 0 along with VGS greater than 0. So, for the conduction of the MOSFET, to have some current in the MOSFET, we need to have VGS greater than or equal to VT naught as well as VDS greater than 0. Now, look at the diagram. In this diagram, VGS is greater than VT. In fact, if substrate is not biased, means substrate is 0 biasing, means grounded, and VD is connected to positive terminal of the battery and source is grounded, and this VG is taken with reference to source, then we can write VGS greater than VT naught. Not because substrate is not biased, substrate is at ground. If VGS greater than VT naught and we have applied VDS, in fact you can write it VDS, which is greater than 0, it is connected to the positive terminal of the battery. Then in this condition, this positive terminal, this positive voltage will attract the electrons of this channel. In this region, in this channel region, in this surface inversion region, there are so many electrons are available, and a conducting path exists between source and drain. So, this positive terminal of the battery attract electrons, and electrons will move from source to drain. So, this is the direction of movement of electron, this is the flow of electron. So, flow of electrons from source to drain. So, if you are standing at this terminal, if you are standing at the drain terminal and looking to the channel, then this terminal is treated as source, means electrons are coming from that portion. So, electrons are coming from source and it is draining from this terminal. That is why it is called as source terminal, it is called as drain terminal. So, electrons are flowing from source to drain. So, path of the electron movement is from source to drain, and the path of current will be opposite to the flow of electrons. So, current conduction takes place from drain to source, and this is called as drain current. This is known as drain current. In this situation, parallelly I am trying to draw the characteristic curve. So, if I have taken VDS at horizontal axis at x axis, VDS is taken at x axis, and at vertical axis if I have taken ID, then initially if VDS is positive and VGS is greater than VT, then the relationship between VDS and ID is found as linear. As I am increasing VDS, current will be increases linearly. So in this situation, MOSFET is said to be operating in linear region. So this is called as linear region operation of the MOSFET, because we are having a linear relation between ID and VDS, and VDS is exactly proportional to ID. Our ID is proportional to VDS. If we increase VDS, current will be increased. Now further VDS is further increased beyond the saturation point. Any VDS is, means VDS is, I am increasing VDS, I am getting more and more current. So this is the relationship between VDS and ID. Exactly linear relation. With increasing VDS, electrons are draining from source to drainant. We reach a point where this channel is just available. So this point is called as pinch off. At this point, we are getting maximum current. So this is the pinch off point. Here I am getting maximum value of current. So when VDS is equal to VD set, means VDS is equal to VGS minus VT. At this situation, we are having pinch off condition. Channel is just available. Beyond this voltage, beyond VD saturation, if VDS is further increased, then this channel will not be available more between the source and drain. In fact, this channel will be modulated. So at this point, we are getting maximum current. After VGS, if we further increase VDS, in fact VDS is increased beyond the saturation point. If VDS is increased beyond the saturation point, then this channel length is modulated. And now electrons are having high kinetic energy. Electrons are having high kinetic energy. They have gained the velocity beyond the drift limit, and they do not need any conducting path among source and drain, and these electrons are drifting from source to drain, and value of current will be saturated, and it attains its maximum value and it will be maintained. So we are getting the characteristic curve like this. The current equation, the value of current will be saturated. See, this is the value of gate to source voltage at which the entire conduction is taken, entire operation is taken. So this is the point where channel length is modulated and the value of current is saturated. So beyond the pinch off point, if we are increasing VDS, then current will no further increase, but channel will be modulated. What happens if we increase further VD saturation? If we further increase VD saturation, then it will have no any effect on the conduction process, because now in this situation where electrons are having more and more kinetic energy, they have crossed the drift velocity limit, then there will be no any effect of VD sat. In fact, saturation voltage is not a controlling parameter for this electron. The only controlling parameter is now VGS. So we do not increase the value of VDS beyond the VD saturation, because if our going value of VDS beyond the VD saturation, then this electron which is moving with high kinetic energy can go inside the oxide, can go inside the substrate, it can go anywhere, because there is no controlling on this movement of electron by VDS. VDS is no more controlling factor. So if we want more current, if we wish to have more value of ID, then instead of increasing VDS, because VDS have no any effect on the value of current, it is a beyond saturation point. So if we want more value of ID, then we have to increase the value of VGS. Say threshold voltage was 0.7 volt and we have a channel at 0.8 volt and we have reached the maximum value of current. Then at VD set, current is saturated. I want to increase ID. Then we have to increase VGS. So say this is VGS 1, that is 0.8 volt. We have increased VGS again. Channel is again created at VGS 2. Channel is again created at 0.8 volt. Again we have increased VGS. Again the same characteristic curve is found. If we want to increase current more, then again we have to increase VGS. At next value of VGS, we are having same scenario. So this is the characteristic curve which is plotted between VDS and ID. This region of this curve from this point to origin is known as linear region. From this point to this point, this curve is called as linear region, and such mode of operation where channel is created, where channel is available is known as linear mode of operation. Where the saturation point is reached, where the current is saturated, then this region of this characteristic curve is called as saturation region, where the current is saturated, and the MOSFET is said to be working in saturation region. So now I am writing the conditions when saturation and when linear region is available in the MOSFET. I am just writing the conditions of saturation and linear mode of operation. Condition 1, when VGS greater than or equal to VT, channel is created, but VDS is, now I am using eraser because I have to write all the conditions. I am writing all the conducting conditions of the MOSFET. So condition 1, when VGS greater than or equal to threshold voltage, but VDS is 0. VDS is not applied, in fact it is grounded, and VDS is equal to 0. Then MOSFET is working in the cutoff mode. Then MOSFET will be in cutoff mode. Cutoff mode means there will be no current, ID will be 0. VGS is greater than VT, but VDS is 0. It means we are having no current. MOSFET is in cutoff mode. There will be no current. Now the second condition. VGS is greater than VT naught. It's a necessary condition to be MOSFET in a on condition. If we are having VGS less than VT naught, then definitely MOSFET is in off condition and it's no possibility of current conduction. Now the second case, where VGS greater than or equal to VT naught and VDS greater than 0. It is applied greater than 0, and the second condition is VDS is less than VD saturation. What is the value of VD saturation? The value of VD saturation is VGS minus VT. So if VDS is less than VD saturation, it means if VDS is less than VGS minus VT, then MOSFET will operate in linear region. Then MOSFET will operate in linear region. Linear region operation means current is linearly varying with applying VDS. So this is the linear mode operation of the MOSFET. Now the third condition. When VGS is greater than or equal to VT naught and VDS will be equal to or greater than equal to or greater than VD saturation. VD saturation means VGS minus VT naught. If VDS is greater than or equal to VGS minus VT, then MOSFET will operate in saturation mode. Then MOSFET will operate in saturation mode. MOSFET will operate in saturation mode. Saturation mode means now current is saturated, there will be no effect of varying VDS. If we want to increase the ID, then we have to increase VGS. So these are the three modes of operation of the MOSFET. First one is cutoff mode, when VGS is greater than VT naught, when VGS is greater than VT naught and VDS is 0, then MOSFET is in cutoff mode. It is in cutoff region, there will be no current, ID will be 0. When VGS less than VT naught, VGS less than VT naught, VDS is applied, value of VDS is positive, but VDS is less than VD saturation, means VDS is less than VGS minus VT, then MOSFET will operate in linear region, means as we increase VDS, we are having increment in ID. Yani VDS means VDS and ID is having linear relation, VDS is exactly proportional to ID. Now the third condition, MOSFET is in saturation mode. Here VGS greater than VT naught and VDS will be equal to or greater than VD saturation, means VDS is equal to or greater than VGS minus VT, then MOSFET is in saturation mode. There will be no effect of increasing VDS. In fact, with VDS current is saturated and it has attained its maximum value. So now come on to the characteristic curve. There are two controlling parameters. In fact, we have seen that VGS and VDS, there are two controlling parameters, there are two voltages which controls the current between drain and source. So this is characteristic basic current voltage characteristic curve for n channel MOSFET, for n channel MOS transistor. On horizontal axis, we have taken drain voltage, VDS is taken at horizontal axis, and on vertical axis we have taken ID. So drain current is taken at ID. This characteristic curve is also called as drain characteristic curve. This is also known as drain characteristic curve. So now we can see that initially with positive VDS, as we are having VDS greater than 0, initially current is increased beyond this point. Here we are having linear variation of current with VDS. Beyond this point there is saturation. So this is the pinch off point. This is the pinch off point. After that current will be saturated. So these are the pinch off point. So this is the drain characteristic curve where the curve is plotted between VDS and ID. In saturation mode, we are having this current equation. Sorry, we are having the current equation. ID is equal to mu n CUX by 2 into W by L VGS minus VT whole square. If we are taking current on y axis, and this is basically constant, you can see some written as C, and VGS is taken at x axis, x minus something constant, then y is equal to Cx square, means upward parabola. So when VGS is taken at x axis and ID is taken at y axis, this is the circuit diagram for the operation of MOSFET. Substrate is not biased, means VB is 0, source is connected to the ground, at drain end we have applied positive VDS, at the gate we are varying VGS. Having variation in VGS, we have plotted this curve. In this diagram we have plotted the characteristic curve by increasing VDS with constant VGS. In fact, in this diagram, this is, just a minute, this is MOSFET, this is drain, this is source. Source is basically grounded with any resistance or without resistance. This is gate voltage. Gate voltage is positive. Positive VGS is applied, and drain voltage is also positive. Now we are trying to make some simple arrangement and just to study the characteristics. So source is grounded, drain is connected to the positive terminal of the battery. This is VDS, positive VDS, and here we are increasing VDS and not varying VGS. So VGS is fixed. For the fixed value of VGS, we have plotted this curve. So here we are varying VDS. So this curve is plotted between VDS and ID having constant value of VGS, and in this curve the variable parameter is VGS. So when VGS is less than VT, there will be no current. Basically MOSFET is off. When VGS is greater than VT, we are getting parabolic increment in the current according to this equation. Because with this equation we are having upward parabola. ID is basically proportional, ID is equal to Cx square. We are having the equation of parabola like y is equal to Cx square. This is known as transfer characteristics of curve, which is showing the working of MOSFET in saturation region. Basically VDS is greater than VD saturation. This is the current equation for the MOSFET written for different region. When MOSFET is cut off, means when VGS is less than VT, then current ID will be 0. In fact, ID is 0 even when VGS is greater than or equal to VT naught if VDS is equal to 0. So this is the first equation when current is 0. The second equation is for linear region. When VGS greater than VT, VDS is less than VGS minus VT. Then this is the linear mode operation. This current equation is for the MOSFET which is working in linear mode, either linear region. This equation is for saturation mode, where the MOSFET is working in saturation mode or saturation region. Another effect is taken here. It is the effect of channel length modulation. So we will study further what is the effect of channel length modulation. So now these are the current equations derivated for p channel MOSFET. Some conditions are reversed. For the p channel MOSFET, we have to apply negative VGS. So for VGS greater than VT, there will be no current. For p channel MOSFET, to operate in linear region, we should have VGS less than or equal to VT and VDS greater than VGS minus VT for the p channel MOSFET. So these equations are derivated for p channel MOSFET. P channel MOSFET means substrate is N type. We are having N type of substrate. Above this substrate, oxide layer is created. A metal gate electrode is also created, and the drain and source region will be P plus. So this is p channel MOSFET. Some metal contact is there, So this can be drain, this can be source, this is gate, and this is substrate. So this is p channel MOSFET. In p channel MOSFET we are having n substrate, in n channel MOSFET we are having p substrate. So these kind of questions are calculated, derivated for p channel MOSFET. So these are the references. We have taken some contents from Benji's treatment. Also, some concepts can be studied from SM Kang book CMOS Digital Integrated Circuits and Design. It's from McGraw-Hill publication. And also you may refer D.A. Neiman and Cedra Smith for further study. So these are the references. That's all. Thank you.